We have an electron gun in a television tube. So yes, the old school big blocky televisions. The electron gun is to accelerate electrons from rest to 3.0 times 10 to the 7th meters per second within a distance of 2 centimeters. What electric field is required, meaning just what strength of electric field would be needed, and also should the electric field be in the same direction or opposite direction of the electron's motion. So let's go ahead and say our electron here is moving to the right. So it starts at rest, and it needs to be traveling 3.0 times 10 to the 7th meters per second within a distance of 2 centimeters. So we'll just say it's moving to the right, just to make it easy on ourselves. So electric field. The electric field is what is causing the force. So force, we know, is Q naught times the electric field. But from Newton's second law, we know the force is also equal to ma. So the magnitude of the electric field is simply going to be ma over Q naught. We know the mass of the electron, we know the charge of the electron, we can figure out the acceleration, we know the initial velocity, we know the final velocity, we know how far it takes to go how far it moves. So our kinematic equation without time would be the one that would be most helpful. Our initial velocity was 0. It said it was accelerating from rest. Let's go ahead and just call our initial position 0. So our acceleration, if we divide by 2x, that will be our acceleration. So our final velocity is 3 times 10 to the 7th meters per second. We need to square that. All over 2x is the distance it moves, so 0.02 meters. So the acceleration of this electron ends up being .25 times 10 to the 16th meters per second squared.
Is that even faster than the last problem?
It is even bigger, I think, than the last one we did. So our electric field depends upon the mass of our electron, which we know, 9.11 times 10 to the negative 31 kilograms. Our acceleration, which we just figured out, over the charge of the electron. I'm using just the magnitude to get the magnitude of the electric field. We'll talk about the direction in a second. So that's the magnitude. That's how strong the field needs to be. 1.28 times 10 to the 5th newtons per coulomb.
Yeah, isn't that television too charged like 20,000, 30,000 volts? I mean,
I'm not sure, actually.
it's some obscene.
It probably is, I would imagine. Direction. What direction does the electric field need to be in our picture in order to accelerate our electron to the right?
Away.
Can you be a little more specific for the way?
Away from the motion.
Okay. So the electric field needs to be this way.
Just like on the light.
Exactly right. Remember, the force on an electron, force on a negative charge, is always opposite the electric field. If this charge is accelerating, speeding up, going faster, then it's moving in the direction of the net force. The force has to be opposite the electric field for a negative charge, which is what our electron is. It's a nice little negative charge. Ask.
I was writing down, how did you get the directions?
We know the force on the electron needs to be to the right, according to the way we've drawn the picture. The force on any negative charge is always opposite the electric field. So the electric field had to be to the left.